Thank you for coming. I think this looks like the Society of Introverts. You know, everybody's kind of spread out. This giant room, and you got little clusters of people. When I first presented this talk to my colleagues, I was basically rehearsing it for them, and I put up this title slide. The first comment that came out was, "So you're presuming that there are good parts?" So the reviews are not good. These are actual quotes from prominent people in the C++ community. It is now accepted by the C++ community that allocators are fairly useless. They are painful to work with. Next, here we go. All right, this one is my favorite from Scott Myers. The standard committee has emasculated allocators as objects. Now, I don't know about you, but when I hear the word emasculated, those are kind of fighting words. One of the most mysterious parts of the standard library. And my favorite, if it ever comes up, a major contributor to climate change. So here's my thesis. With some guidance and with borrowing some features from C++ 17, we can make allocators both useful and usable. So we're going to be talking about these things today, really why allocators exist, going down through actual kind of semi-tutorial on how to write an allocator and how to write a container that uses allocators. So let's start with the why. So this is I forgot what the count was, a 236th talk on allocators at this conference, something like that. Seems to have become a theme in the conference, and it was not coordinated. Unfortunately, we should have coordinated. We have less overlap. So all of us say, why do you want allocators? So here's an analogy. It's why we want allocators. When you are checking out from a website, like say Amazon in this case, and you want to pay for the purchase, you have to tell it how you want to pay. What is the credit card you're going to use, or debit card, or whatnot. And there may be a default, but you get to choose your own. To the vendor, it doesn't matter, right? Money is just money. They're going to get their money, they don't care. But to you, it may matter, because one card may have rewards points, another card may be for your business purchases, one for your personal purchases, one that you don't want your spouse to know about, you know. So the credit card is kind of a customization point. It lets the purchaser customize the transaction. Most of the transaction is taking place on that side, but there's this little piece that you say, call me back, get the money out of here, allocate the money from here. So allocating memory is kind of like that. The container doesn't care where the memory comes from. It just says, I want a source of memory. But the user might want some control. And why would the user want control? Well, there's a bunch of things here, and this is a very incomplete list. But it could be that you have an allocation pattern specific to your use. You know that things are going to be allocated in certain clusters and things like that. You may want to keep similar things together in memory for locality purposes. Special purpose memory, this is becoming bigger and bigger. Persistent memory, high bandwidth memory, things that may be either limited or have very special characteristics. Thread locality, so if you know that your whole application is running in one thread, or you know that all of the allocations and deallocations are going to come from the same thread, you'll save overhead by using a thread local allocator. And then one we'll be talking about more today, statistics gathering and other kinds of instrumentation, so you know what's happening with your memory. The core functionality of an allocator, though, is simply to allocate and deallocate memory. Give me some memory, here's the memory back. And of course, you know, if you don't give the memory back, you're not being a very good citizen, although there are situations where it doesn't really matter. So C++ takes this core functionality, and then we add layers of complexity to it. Okay, so I should introduce myself. Until we get to this point, I was kind of hesitant to do so. I am responsible for a lot of the allocator stuff in the standard. So, but only the good parts. Okay. The stuff that was written in 1998, that was before my time. So the complexity Unfortunately, I am responsible for some of the complexity. In fact, a lot of the complexity. My name is Pablo Halpern. I work at Intel, and before that, I worked at Bloomberg. And at Bloomberg, we had a lot of need for using special purpose allocators, and that is where a lot of the work got done that ended up getting proposed into the standard and eventually adopted. And we didn't really finish the job until C++17. And C++17, I can finally say, allocators actually have good parts. So, if the purpose of an allocator is simply to allocate and deallocate memory, then where does all this complexity come from? Well, it started at the very beginning. In 1998, when the first standard was created, allocators were invented to solve a very different kind of problem than we have today. Mostly near and far pointers with the x86, the 8086 memory model. It did have aspirations to being a more general customization point, but didn't really fulfill those, and they kind of ran out of time to make it good. So we made a bunch of improvements in C++11 and had to add a bunch more complexity in order to keep backwards compatibility with what we had standardized in 98 and 03. One of the pieces of complexity that comes is the fact that it is a template argument. The allocators are template arguments to your containers. This causes your code, if you want to be able to take a vector using any kind of allocator, it means that your code now has to be a template because the allocator is a template argument. So to some extent, there was too much generalization, and I am partially responsible for that. Too much generalization trying to please too many people. In my defense, I'll say it's possible we would not have gotten the improvements had I not pleased enough people. So take that for what it's worth. But today, we're going to try and get past all that complexity. So in C++11, we made it easier to create allocators, but we made it harder to implement containers that use allocators. When I say we, I mean I, but not really just me. There were other people who were complicit, should I say. All right, so the STL containers always talk to the allocators through this allocator trait. So we added this layer of template indirection. It's not runtime indirection, but it's simply template indirection in order to get all the features that we wanted in C++11, but still have C++03 allocators work in the new model. And we added all this flexibility for whether allocators propagate when you copy an object, move an object, and so on. There are a lot of type defs. There's this rebind template that was invented in 98, and we had to sort of keep some semblance of it in 2011. There's this generalized pointer model that lets you create these special fancy pointers. It can be very useful when you need it, and they're totally in the way when you don't. The allocator type is a policy argument to every container that uses it. And then we have this allocator traits, adding one more layer. So my thesis is that we're going to limit ourselves to a subset of this. Certain allocators and certain allocator usages will not work with what I'm about to talk about, but the lion's share work, our experience at Bloomberg using this model is that it works for a lot of things and you get a lot of benefit out of it. Here's the mess we inherited. This has to do with the way allocators are propagated when you copy an object, copy construct an object. So I'll walk you through this code a little bit. I don't know where to put my laser pointer here. There it is. Okay, so this first line declares this custom string class whose allocator is this custom allocator. Now the custom string is just oh, this is a typo. This should be basic string, I'm sorry. So it takes basic string and it says basic string with char, and this char traits, which is one of the most useless things we ever added to the standard, and then the allocator, which was at least at one time considered the second most useless thing that we added to the standard. So in order to specify the allocator for a string, I have to go all the way back to basic string and give it all the template arguments. And then I have my custom allocator, which I don't describe on this slide, but just is some kind of custom allocator type template. And we create 3 allocators. And you don't need to care too much about what the constructor arguments are here, except to know that they're clearly 3 different instances of the same type of allocator. Okay, so when you're talking about templates, you just have to be really careful about when we're talking about types and instances. So these are 3 instances of the same type. And then we create 3 custom strings, one using each of the 3 custom allocators. All good so far? And now finally we create a vector containing these strings. Now the first thing we want to do is push a string back. And when we do that, the string gets created with the same allocator as where it came from. So x1 has alloc1. Therefore, a copy of x1 ends up in our container with using allocating memory from alloc1. Good so far? Same thing if we do another pushback with x2, which uses allocator 2. Now things get interesting after this. First, we're going to reserve some space, and then we're going to insert at the very beginning of the container another string using a different allocator. First thing that happens is that we have to make room for it. So it copy constructs the second element into the 3rd slot, and it uses the same allocator. Then it then it assigns the first element into the 2nd slot. Ooh, something interesting just happened here. The assignment did not move the allocator. That's because assignment never does, and never should. Interesting. So now we have a copy of x1. We have 2 copies of x1, one that uses allocator 1 for its memory, and the other that uses allocator 2 for its memory. And then finally, we assign x3 into that 1st slot, and its allocator is nowhere to be found because assignment, again, does not move the allocator. So I know this is a fairly subtle point, and it's not something we really need to dwell on, but if you're like me, this is what you think when you see this diagram. It's like, could this possibly have been intentional? I mean, my answer has got to be no. I mean, we didn't deliberately set out to create this kind of mess. What we really would like is something more like this. This is the scoped allocator model, where the same allocator is used for the container and then is passed down into all of the elements that are inserted into that container. Hopefully all the way down recursively through anything that uses allocators. So this is kind of our ideal setup. If we have our container, it has an allocator. All the memory for the container comes from the allocator, and all of the memory for the strings within that container come from that same allocator. This is the scope model. It's kind of our ideal. In C++11, we added the scoped allocator adapter, which makes this possible. You wrap your allocator in this adapter, and now, so long as everything uses an allocator, uses the same type of allocator going down, it will pass the allocator down. In C++17, we added polymorphic allocator, which not only makes it possible, but actually makes it easy to do this. So let's look at the simple model and set aside all that complexity for the moment. The model that we introduced in C++17 is this polymorphic memory resource. It's a new namespace, PMR, and it has in it the memory resource type, which is a base class for creating your own memory resources. And then there's a polymorphic allocator, which is simply a wrapper around a pointer to the memory resource. It is an allocator in the full C++03 sense of the word, so it plays nicely with vector and string and anything else in the standard and outside the standard that uses the existing allocator model. Then we also have a vector in that PMR namespace, which is just an alias for the existing vector, but where we hard code the polymorphic allocator as the allocator type. So that makes it really easy to create a vector using a polymorphic allocator. You don't have to wait for C++17. Oh, so the same thing is true for the other containers, by the way. You don't have to wait for C++17 to get these features. There's a link here to my GitHub where I have C++11 implementation of all of these features. So I welcome you to go there. It's using the Boost license, so you're free to use it. Let's dive in a little bit into the different classes that I just mentioned. Polymorphic memory resources. This is a base class. Like I said, it is a pure abstract base class that has as its core these three functions: allocate, deallocate, and isEqual. Allocate and deallocate obviously being the main business end of the thing. isEqual is a special thing that we needed just to make everything kind of stick together. These functions are not virtual functions, but they delegate to virtual functions in the protected space. There's a doAllocate, doDeallocate, and doisEqual. And those are the things that you override when you derive from this class. That's kind of a pattern that shows up in the standard. String buff uses the same pattern, these protected virtual functions. I won't get into why we do it that way. I don't say I completely agree with the pattern, but it is a pattern. Polymorphic allocator is this wrapper I mentioned around the memory resource. So let's take a look for a minute at the constructors. The default constructor uses the default memory resource. Now, what is that? I haven't mentioned that yet. The default memory resource. Well, you have a potentially open-ended set of possible memory resource types derived from the memory resource base class. But there are a few that are provided by the implementation, by the standard, including one that simply uses new and delete as a way of getting memory. And that one is, by default, the default. What I mean by that is that you can actually change the default. You can set it, but you usually don't. So if you don't do anything special, then the polymorphic allocator with no arguments in the constructor will get the new and delete allocator, which is pretty much what most people, I think, would expect. And then the second one is a conversion constructor from a memory resource pointer. So notice that it's not explicit. It can be used for implicit conversions, and we take advantage of that a lot, as we'll see when we actually get to the use cases. That's it for our important constructors. Now it's got copy constructor and move constructor and assignment and so on, and those things are just defaulted. Resource is an accessor that simply returns the resource that you passed in or that you got by default when you constructed the polymorphic allocator. And then you've got the important things that make this an allocator, an allocate, and oops, wrong button. An allocate and a deallocate function. And these signatures note return T's, or TPs in this case. They return the type that the allocator is instantiated on. Now, I'll contrast that to our memory resource, which the allocate and deallocate functions, notice, return generic pointers, or work with generic pointers, void stars. So these just allocate bytes, aligned correctly because you have an alignment argument, but it's just bytes. Whereas the C++98 model, hit the wrong button, returned these T-stars, and that's actually part of the problem in their usability, because you almost never need a T-star. Almost never. What you need is something like a node that you're constructing. So this actually just kind of gets in the way, and then you have to rebind the allocator, and it's a mess. Just raw bytes is so much easier. So now I'm going to step away for a little bit from the actual standard and say, this is something I'm encouraging you as an idiomatic thing, and something that we're actually looking to quasi-standardize. And I say quasi-standardize because the standard cannot standardize idioms, but we can make it easier for idioms to be used. So there are proposals from me for making this a little bit easier to use. But it's pretty darn usable already. Polymorphic allocator of byte. So first of all, what's byte? Byte is a C++17 type that it represents a byte. Got it? Good. If you use that as kind of your one true allocator type, then you have a vocabulary type. You have an easy way of passing allocators around without using templates, and it does everything you need. You allocate bytes out of it, you get bytes, you return your bytes to it. Easy. It's a scoped allocator. So that diagram I showed you of the vector containing strings where everything is coming out of one allocator, this makes it really easy to use. You just pass this thing through. Direct byte allocation through the resource, and it's better than a raw pointer to a memory resource because it has a reasonable default initialization. So that's really useful. If you put an allocator at the end of your argument list for your constructor, you can just default it to open, close, curly, and you'll get some reasonable default. Whereas that's not true for a pointer. Pointers don't give you reasonable defaults, they give you null pointer, and null pointer is not a good memory resource pointer. You can't be reassigned by accident. Remember I said that once a container is constructed, you should never change the allocator in it. Well, if you accidentally allow the default assignment operator to get generated, you may end up with a serious bug, and something that you might not catch right away. That can't happen if you're using this polymorphic allocator. It doesn't have a public assignment operator. And it plays nicely with the rest of the standard library. It is an allocator. Whereas a memory resource is not an allocator, it's a resource. It's a thing that's expected not to be copied at all, but exists to give and receive memory, and you pass a pointer around to the single object. By the way, the memory resource is really formalizing in the standard something that has always been true of stateful allocators. Allocators that contain state, they almost never contain anything other than a pointer to some thing that is shared among all of the equal allocators. So things have gotten a lot easier. In C++98 and 03, to use an allocator was pretty easy, but you've got this problem of the viral templates, where if you want to be able to accept, say, a string taking any allocator, instead of simply writing string, you have to write basic string char, type traits char, allocator char, where the allocator is a template argument that comes in to your argument list. Creating an allocator, again, pretty easy. There's a lot of boilerplate you'd have to copy. If you get the rebind wrong, you're in trouble. People get the rebind wrong all the time because they try to inherit from std allocator. Really, really bad idea. Creating a scoped allocator, as far as I know, not possible. Just did not have the facilities in the standard library to work with a scoped allocator. Creating a new allocator-aware container, not too hard, but you had to be careful. You had to worry about the rebind stuff. And in C++98 and C++03, the container could assume that all allocators can pair equal, which means you couldn't really have state in your allocators, which really limited their usefulness. In C++11, we made some things easier and some things harder. Creating an allocator has now become really easy. You basically just have to write allocate and deallocate and declare your value type. Creating a scoped allocator has become not only possible, but really not too difficult because you simply use this scoped allocator adapter. It's a big template, but you just make a type def for it and you're all good. And creating a new allocator-aware container, well, we made that harder, unfortunately, because now you've got allocator traits to work with and propagation traits. But then in C++17, which is available to you now through that GitHub repository, we made all of these things easy. Creating a new allocator is as easy as just deriving a new memory resource. And the polymorphic allocator is already scoped for you. And the most important thing, which I'll point out, is the lower right corner. The allocator-aware containers can skip all of that complexity. If you're willing to stick to the idiom, that polymorphic allocator of byte is the be-all and end-all of allocators. So we're going to get to that right now. Building a new memory resource. So we're going to do two things. We're going to build a new memory resource, which gives us the power of creating a new allocator. And then we're going to build a container that uses polymorphic allocator. And we're going to see how easy or difficult those things are. So the memory resource, don't create a new memory resource necessarily, because there are some in the standard. Now this is one place where I can give you only limited help, and the reason is that I don't have currently on my GitHub repository implementations of these things. They may be out there. I ran out of time to research them, but these are what's in C++ 17. So new delete, the wrong button again. That one is in fact in my implementation. It had to be, I needed the default. So it just allocates using operator new, nothing special, it's the default. The null memory resource throws when you try and allocate. How useful is that? Well, surprisingly, it's really useful. And the reason is that if you have any kind of arena or pooled allocator that comes with its own memory, and when that memory is exhausted, it's supposed to throw rather than get more memory off the heap. These other three resources all are chaining, which is to say they have an upstream memory resource that they get memory from when they run out of their own internal pool. And so what do you chain when you have a fixed size buffer and you want to make sure you never exceed it? Well, you chain it to the null memory resource. And then you'll get an exception if you actually exhaust your fixed size buffer. I'll talk about chaining when we actually implement our own here. All right. We start getting to the actual truly useful ones next. The synchronized pool resource. This allocates objects of similar size together into these fixed size pools, not fixed size pools, but pools of fixed size objects. It gives you good locality, and for most containers, you end up using just one or two pool sizes. So it's very efficient. It packs. There's very little fragmentation in memory when you use a pool. It's synchronized because it's thread safe. Two containers using the same resource will not stomp on each other. The unsynchronized one is exactly the same thing, but it's not thread safe. That gives you some performance benefit because you don't have mutexes involved. And then the monotonic buffer resource, that is also not thread safe. This is a memory resource that the space it takes up grows in one direction. It doesn't shrink, which means that the deallocate is an empty function. It doesn't deallocate anything. Why is this useful? Well, because allocate is wicked fast. I'm from Massachusetts. I get to say wicked fast. So when you allocate memory, all it does is it moves a pointer down the buffer. That's it. Can't be any faster. There's one check to see if you've reached the end of the buffer and if you need to get more. That's about it. It's extremely fast. The consequence, though, is that we're not keeping track of anything we've allocated, so we cannot deallocate something in the middle. Why is this useful? Because most of the time what you do is you create a container, you build it up, and then you throw it away. So I would say that at least half the times with containers, you don't ever delete objects. You never remove an object from the container, you just build it up. You're creating up a set of something, and when you're done, you're just throwing it away. In which case, I don't care if you're going to throw it away piece by piece. Actually, I do care. I don't want you to throw it away piece by piece. That's expensive. Throw it all away all at once. In fact, maybe don't even call it destructor. If the only thing that the elements in the container are using is memory, then you don't need to call it destructor. Simply throw the memory back, give the memory back to the global pool. The buffer resource, you give it a buffer initially, and that buffer could be on the stack, which is an extremely efficient way to do it. Okay, but none of those meet our needs. So we're going to write our own. And this is the purpose. The purpose of this allocator is for testing. So it is a test allocator, or a test resource, sorry. So I'm going to keep accidentally saying allocator when I mean resource. Just remember that the allocator is the handle to the resource. And so when I'm saying allocator, I'm usually talking about the resource. The resource is what we're actually putting the effort into. The allocator comes for free. It is simply polymorphic allocator of byte. So the purpose of our test allocator is to keep track of how much memory is allocated, deallocated, high water marks basic statistics on memory usage. We check that every deallocation matches an allocation. That will flag when, for example, we delete something twice or we delete something from the wrong allocator. Check for memory leaks. So if the resource is going out of scope and there's still memory allocated from it, it first of all reclaims it, but also tells you that it's done so, because you should typically be doing that. And again, the source is in the same place as the other sources that we've been talking about. So this is our test allocator. Good. Our interface. It's a test resource. It derives from memory resource in the yellow there. Publicly derives from it. It has a constructor. This slide is a little old. It says parent. The typical term that we use in the standard is upstream, so instead of parent. So there's upstream resource. So it's going to get its memory from this resource that's provided, and by default we get the default memory resource, which is this static function up here. Sorry, not static, but namespace scoped function that returns the current default memory resource, which is usually the only default memory resource, which is the new delete resource. We don't care about the destructor too much. We have a function that returns the parent or the upstream resource. And then we've got our statistics functions. The number of bytes allocated, deallocated, and so on, as you can see. And then these three static functions at the end are for tracking if memory has leaked. And the reason we do it that way is because the place where we discover leaks are in the destructor, and throwing an exception from the destructor is generally a no-no. And it's not just, in this case, it's actually not something we could do. Because even if we wanted to declare a throwing destructor, we can't, because the base class does not have a throwing destructor. And the destructor is virtual. The protected section of our class has our three important overrides. Notice that we did not, in the public interface, have allocate, deallocate, and so on. Those are inherited from the base class. In the protected place, that's where we actually override the virtual functions. Do allocate, do deallocate, and do is equal. In order to keep track of our allocations so that we can match deallocations with allocations, we have this simple record that records every allocation, the memory that was returned, the alignment, and the size of that block of allocated memory. So we can look for mismatch. And then our private data members, I can go into this implementation, but basically we have to have a pointer to our parent or upstream resource, a bunch of things to keep track of statistics, and then this vector here of the blocks that we allocated, so it can keep track of everything that we allocated. Now, I've seen this implemented where on every allocation there's this extra piece that is allocated at the front, and we keep the statistics for like a linked list of currently existing. That is actually, looks really efficient and actually is really hard to write correctly. You get alignment stuff, and with things that have big alignments, you end up wasting a lot of memory. I think it's actually more efficient to keep a separate vector of those things. But it's certainly simpler. And notice that this is a PMR vector. So it is going to use this PMR polymorphic allocator as its allocator type. And that's going to be, you'll see that that'll be useful when we get to the constructors. Okay, and then we've got some statics for keeping track of our leaks. Do allocate function. Finally, we get to the business end of this thing, right? So far, it hasn't been too hard, right? It's been pretty much straightforward. But now we're actually doing something interesting. The first thing we do when asked to allocate memory is we allocate memory. Where do we get that memory from? We get the memory from our upstream resource. Obviously, for an allocator that is using some special kind of memory, you're going to have to do something special that may be OS specific. It may be specific to your environment, whatever. In this case, it's really easy because we're not actually doing the hard work of allocating memory. We're just delegating that to our upstream allocator. And then the rest of this is simply keeping track of what we've done. All right, we keep track of the record, how many bytes we allocated and what the return was, and we bump our counts. I'm not going to spend a lot of time on the actual work that this thing is doing because it's not the point of the talk. But okay, we're bumping our counts, and then we return the memory that we allocated. Do deallocate is pretty much the same in reverse. The only difference is we've got this big if statement in the middle where we are checking to make sure that everything is valid, that we're not deallocating something that we didn't allocate, or we're not trying to deallocate a different number of bytes or different alignment than what we allocated. And then we return the memory to the upstream resource. And then get rid of the record that says this thing was allocated. It's no longer allocated, so it's gone. Okay, and update our statistics again. Good? Now, one that people find a little confusing, is equal. What does it mean for two memory resources to be equal? Well, typically they have to be the same type, and in most cases they have to be the same object. What it means for them to be equal is that you can allocate bytes from one and return them to the other one. And it's pretty rare that you could do that if they are separate objects. They have their own state, and you can't. So in this case of this test allocator, you can't allocate from one and deallocate from a different one. They're keeping track of different lists of what are the valid allocations, and they may have different upstream allocators. So the only way they could be equal is that they are the same object, which means their addresses are the same. And that's what this is doing. Most memory resources you write will have an is equal, a do is equal that looks exactly like this. Just compares this pointer to the other one. You don't even care what derived class the other one comes from. The only way it could possibly compare equal is if it's the same object, which means it's the same type. So we don't have any dynamic cast, none of that. We're just looking at pointer equality. So if that's the case, why do we have an is equal virtual function in the first place? Well, there are exceptions. And the exceptions are important enough that we put this in. And I tried to avoid it, but we couldn't. And specifically, there's an adapter that says take any C++98 or 03 allocator and make a polymorphic allocator out of it, or make a polymorphic resource out of it. And the problem is if you take the same allocator and you do that twice, you get two separate objects that really are equal to each other, but they're different objects. And so we couldn't just make this the default that always works. But it almost always works. There's one other thing that you may write other than this, and that is return true. If your memory resource has no state for some reason, like the new delete allocator, then they always compare equal. So simply return true. So then let's summarize, because really, we're done. All the hard work is done. I didn't show the accessors, those are obvious. They just return member variables or do a little arithmetic. And the destructor is, we don't care. It's automatically generated is good enough. So empty curlies is good enough for the destructor. So we're done. So what did we learn? Well, creating the memory resource is as easy as simply deriving from PMR memory resource. We override do allocate, do deallocate, and that's where we do all the real work. And we override do is equal to test for equality. And this is what I just said when I was looking at the other slide. Generally, you just look for identity equality. Sometimes you return true. In rare cases, you have to do something more complicated. That's it. That's all you have to do to create a new memory resource. How easy is it to use this to now build a container? So let's build a simple container. So our container is going to be this singly linked list. We're calling it S-list. I know it's really original. And it's kind of similar to list or vector, or it's actually closer to forward list in the standard, and it is a singly linked list, forward iteration, and so on. This is the data structure drawn out for you so that when you look at the slides, you understand what we're doing. It's simply a sentinel node at the head of the list, points to to the next node and so on. Each one has a next pointer, and then we have a tail pointer that points to the last node, not one past the last, but the last one. So the important thing to keep in mind about this data structure is that every time you're pointing at a node, you're really pointing at the thing before it. And that is how this is important for allowing insertion and removal of nodes, especially removal of nodes. You need to always be pointing one behind where you're looking. So there's always this extra step of indirection. When the list is empty, it's simply the head node, and the tail points to the head. Come on. There we go. So let's look at our interface here. We have the default constructor. This is the nodes. I'm sorry, this is not the list. These are the nodes data structure. We have a base class that does not contain any values. It just contains the pointers to the next node and so on. So this is what our head will be. And it contains a pointer. You can read the constructors yourself. It's pretty obvious. And then we have a derived class from it, which is the actual node containing the actual value. And now this, what? Union type? What is that about? For those of you who have not read every sentence of the C++11 standard, you might not know about this interesting feature. Unions now can contain objects that have constructors and destructors. Didn't used to be the case. It used to be limited to pod types. Now they can. All right, that's cool. But why are we using it here? Well, when you have an object, a non-trivial object in a union, creating the union does not construct that object by default. So you actually have something containing an uninitialized object, which happens to be exactly what we need for this purpose. What we want to do is when we create the node, we do not want to initialize the object in the node. And the reason that is because we're doing this in two steps. We are creating the node, and then we are somehow collecting the arguments that we need to construct the object inside the node. And those are two different things done in two different places, and it would be really a pain to combine them. So instead, we say, okay, when we create the node, let's not initialize the object inside of it. Instead, we'll leave it uninitialized and we'll initialize it later. It's an anonymous union, so this M value has this nice feature that looks just like any other member variable when you access it, but it's uninitialized after we construct our nodes. Everybody clear on that? Really, really useful thing. We used to be able to do this in C++03 using this uninitialized buffer thing where it would create a union that had something correctly aligned, but didn't actually contain the object. It was a fairly complex template, not too hard to use, but this is easier. Now, let's look at our actual implementation. We have our head, which is this node base, pointer to node base, our tail pointer, our size. We always have to keep track of size because typically you want your containers to be able to return their size in constant time, which means you can't just count the elements, which would be order n. And we're have our allocator type. Our allocator type I feel like I'm missing a slide. Okay, they're kind of out of order. All right. Our allocator type is in this blue box, the last thing in the blue box. It is hard-coded as polymorphic allocator of byte. Hey, we have our be-all and end-all allocator in here. All the rest of the stuff in that blue box, including the allocator type, cut and paste. Write it once, you never have to write it again, you just cut and paste it. Exactly as it is here, you don't have to customize it for TP or template arguments in any way. This is just boilerplate for a container. We do need to specify our value type at the top, and our iterators. We're not even going to go into how the iterators work because they have nothing to do with allocators. But if you go to the GitHub repository, you can see how they work. Basically, pointers to nodes. Our constructors. Notice something about our constructors. Every constructor takes an allocator or has an overload that takes an allocator. So in fact, in this case, we have both. So our default constructor is this thing here. It can be called, it can be invoked without any arguments, and you'll get the default allocator, which uses the default resource, which is new delete. Or you could specify an allocator, optionally. Our second argument, our second constructor is a copy constructor. If you do not pass a second argument, this has the signature of a copy constructor. And it is, in fact, is the copy constructor. But you could also specify an allocator. So you can create a copy of this S list using a different allocator. Then we have our move constructor, no allocator. And then we have this thing called the extended move constructor. So this is the extended copy constructor. This is the extended move constructor. It takes an allocator. And I'll show you why we use different formulations for the extended copy constructor than the extended move constructor. The extended copy constructor and the regular copy constructor are only one constructor, but the regular move constructor and the extended move constructor are two overloads. And we'll look at that in a minute. This is the business, this is where the real business of inserting something happens. If you look at the interface, we have insert front, insert back, push front, push back, insert, and we have mplace front and mplace back and mplace. All of these things, insert objects, they all delegate eventually to this one function, which is the mplace function. Mplace, a term that was kind of coined in C++ 11, add an object to a container, building it in place within the container instead of creating it outside the container and then copying it into the container. So it saves a copy, and it also allows you to use objects that are not copyable. Okay. The important thing here from allocator use is this two-step that we're doing, the secret sauce number one. You allocate the node, and then you construct a value within it. So a couple of things to notice. First of all, when we allocate, we are getting the resource out of the allocator, and we're allocating the raw bytes. Now, the proposal I have in front of the committee is to make it possible to avoid this extra middle step of getting the resource out, but actually having a byte allocate as a member function within the polymorphic allocator. But it's not there yet. This is just a little bit of inconvenience you have to put up with. So we're allocating the bytes, and we're allocating the bytes not for a TP, not for this, but for a node. And that's almost always the case. You almost never allocate memory just for the element that you're inserting, but for some kind of node structure that contains the element you're inserting. But then we ask the allocator to construct the object within that space. But we're not constructing the node, now we're constructing the actual element. Construct should always be called only on the element, not on the node. Okay, it's a subtle point, and it's really a recipe to just keep in mind. Allocate the node, construct the object. Allocate the node, construct the element. We use construct here instead of using placement new, because construct does the fancy stuff. What happened? Anybody know what's going on? So we're using this construct function instead of using the placement new, because the construct function has magic in it, and that magic is if the element that we're constructing takes an allocator, we could pass the allocator down into that element. So that scoped behavior that we're so happy to have comes from using construct instead of just constructing the element. You do not have to figure out the argument list of the element with the allocator. You pass the argument list without the allocator, and the construct function tampers with the argument list and puts the allocator in. Now it's going to get hard if I can't switch sides. So the funny thing is I am seeing it here on this display. So we're just lost. Ah, good. All right. Oh, I skipped over all the rest of the stuff because that's linked list stuff. Harder than you might think, right? But that's what it took. The erase is the inverse. We call destroy. Notice that we're using address of. The reason we're using address of is in case your element type has an overloaded operator ampersand, we don't want to use it. We want the actual real address of the thing. And that's what address of does. So we destroy the object at that address. That's the element. And then we deallocate the node. So exactly the inverse of what we did in the insert case. Destroy doesn't actually do any magic, but it's symmetrical, so use it. It just calls a destructor. Getting to the end here. Okay. The last subtlety here is in our move operations. Well, so right in here we have the copy assignment and the move assignment operations. Okay, copy assignment is really straightforward. It just copies it. Done. All right, just copies every element. Move assignment, the stuff in the box is where it gets subtle. Remember I said that once you put an allocator into an object, a construction, it should never change. I don't have time to explain why that is. Trust me that in all the years I've been using allocators, which is more years than most people have been using allocators, I have never seen a good use case for the allocator changing after construction. Generally, that's a really bad idea. And remember the scoped container? We have, a vector of strings and they're all using the same allocator all the way down. Imagine if you assigned a string into it and the allocator changed, all of a sudden you've broken that. So don't change the allocator on assignment. Copy assignment, move assignment, don't change the allocator. Don't change the allocator in any way, except maybe some kind of reinitialization, which is effectively the same thing as destroying and reconstructing the thing. So our assignment now cares, our move assignment cares about the allocator in that if the allocators are the same, the object that we are assigning to and this object that we're assigning from use the same allocator, we can do this very efficient, taking the guts of the thing we're moving from and putting it into the thing we're moving to, which is the thing we normally want from our move assignment. But if the allocators are different, we can't do that. We actually have to copy everything so that everything gets allocated into the new allocator. Right? And so that's what all this logic here is. It's really pretty simple. You just have to understand why we're doing it. We check to see if the allocators are equal. If they are, we just do a swap. Because a swap is one of these gut-moving things that we do. And if they're not equal, then we do a copy assignment. And there's a little C++11 subtlety here that the other that we're passing in here, hit the wrong button again, here is a normal reference. It's no longer an R-value reference, so we're not recursively calling this assignment operator. We're calling the other assignment operator up here. Okay. Copy and move construction is easiest just to delegate to the appropriate copy and move assignment operators. In the copy constructor, nothing special happening here. If we have an allocator passed in, we use it. If we don't have, where's my laser pointer? I don't see, oh, there it is. There it is. If this thing is passed in, we'll use it. If it's not passed in, we'll get the default allocator. That means our copy, by default, will use the default allocator, our copy constructor. Right? This is something that's a little bit of a matter of taste, but generally we found that it's better not to copy the allocator. But most things do copy allocator on copy construction, so just know that there's a little difference between this and the other standard allocators. The slist constructor for move construction simply sets the allocator, it delegates to the default constructor with allocator, and then calls the assignment operator. So again, then there's some C++11 magic here, one constructor delegating to another constructor. For the extended move constructor, instead of using the allocator from other, we use the allocator that was passed in. So this is an important distinction, an important subtlety. The Copy constructor, you could simply pass a default allocator in. The move constructor, you can't. Why? This move constructor in the middle it always gets the allocator from the other one. Move constructor should always move the allocator. Unless it's the extended move constructor, in which case you specify the allocator. So if you don't specify an allocator, the allocator should be moved. That is not true of the copy constructor. The copy constructor can do whatever it wants. And the simplification we're getting here is that we're just always using the allocator, even if it's a default allocator that was passed in. We can't do that with the move constructor. So we'll put it all together here. Let's write some code that actually uses our new allocator, our new memory resource, and our new list. The code here, I think, is pretty self-explanatory. We create our resource, our test resource. We create our list. We create a string to put in there. It says, say hello. I don't know if you can read that well. Say hello to my friends at the university. I specifically chose a string that was long enough to be larger than any small object optimization I'm aware of. And we assert that we have not allocated anything from our test resource yet. Why? Because this string we didn't pass a memory resource in, so it's using the default resource, which is new delete, and our list is empty, so we haven't allocated anything yet. Then we push the string back into it, and now we say we've got 2 blocks allocated out of our test resource. Why 2? One for the node and one for the string's contents itself. So this is what it looks like in our diagram. We see that everything came out of the same test resource, same allocator, same pool of memory. And so, enough said. So let's summarize here to get it right. Every constructor should have a variant that takes an allocator. And the allocator should be polymorphic allocator of byte. Okay? So here's our example. Now, the example I've shown before with slist always puts the allocator at the end. There are times when you want to put it at the beginning of the argument list. If you do that, you should prefix it with allocator argt. This is an idiomatic use that the standard recognizes so that it knows that the scoped allocator model knows that this is an allocator. That first argument is an allocator. The reason you do this often is because you may have a variadic template. The number of arguments isn't known. You cannot put a fixed argument at the end of a variadic list. Eventually, we may actually be able to, but even then, you wouldn't be able to default it. So, so you put it at the beginning of the list instead, using this idiom. Okay, but just make sure that for everything that doesn't take an allocator, there's a version of the constructor that does take an allocator. The move constructor cannot use the default allocator. It always moves the allocator from the other thing. And so therefore, the extended move constructor is a separate overload. No default arguments there. Move and copy. Copy construction and assignment, nothing special there. For move construction and assignment, we want to move when possible, when the allocators are equal. Don't move when they're not, just copy when they're not. I'm going to finish quickly so I have time for at least a couple of questions before I run out of time. Adding elements. You allocate the bytes, then you construct the element in the bytes. Consistent use of polymorphic allocator. What have we gained? Well, believe me, I would not have been able to spend only the second half of the talk going through how to write a container. In fact, I'd probably need a 2-hour talk if we were doing it without this polymorphic allocator. We don't have this template arguments. The allocator is hard-coded. No need for allocator traits, no need for these propagation traits. We just never propagate the allocator. That really should have been the default. The other propagation traits are really not that useful. No rebind, just allocating bytes. Simple, understandable defaults. So I would normally stop for questions before wrapping up, but we're really kind of out of time, so I'm going to do a conclusion and I'll stay for some questions afterwards. So conclusion. We have historical complexity, but with C++ 17 features, we can ignore most of that complexity. So the trick is leave the complexity behind and just consistently use the new model. If you need to interface with the old model, you may not be able to completely leave the other complexity behind, but if you stick to polymorphic allocator of byte, then you can assume things, you don't need to use the allocator trace and so on. You derive from polymorphic memory resource to create new allocation mechanisms. So, what would these clippings look like using a polymorphic allocator? You would say, it's now accepted that allocators are extremely useful. They're a joy to work with. The C++ Standards Committee added wording that simplifies custom memory allocation. One of the most powerful parts of the C++ standard. And you earn 200 rewards points when you use them. Thank you very much.